iron pipe. But I wouldn't use black iron pipe for just potable water unless I'm the U.S. Navy on board ship, okay? No one in the right mind would use black iron pipe, okay, except NAVC, for potable water, because potable water has oxygen in it. Boiler water actually had oxygen in it when you fill it up, but that oxygen gets consumed, and as the partial pressure of oxygen in that water decreases, it doesn't form rust inside the pipe, it forms more magnetite, okay? At lower oxygen pressures, if I look at the chemical formula for Fe2O3, which is hematite or rust, which has a ratio of 1.5 oxygen to iron, or if I look at Fe3O4, which is magnetite, it's slightly magnetic, has a ratio of 1.33 oxygen to iron. This has a lower oxygen potential, the magnetite, and so if I get below the equilibrium oxygen potential of oxygen in water. What is the equilibrium oxygen potential in water? None of you are chemists, are you? It's 0.21 atmospheres, because that's what it is in air. And if it's in equilibrium with air, how long can rolling waters remain impure as they go over rocks and stuff? Well, they're getting aerated in some of our water treatment plants. They just put ozone or whatever. They oxidize away all the organics. They burn up the bugs by giving them too much oxygen. Okay. But in a boiler system, once you shut it off and make a closed system, you actually generate magnetite. And the magnetite is sort of self-healing. If you get a little bit more oxygen in there for some reason, it'll just form more magnetite if you had a scratch or something, or erosion or something on there. So it's a nice system for closed systems. But for open systems, we either use PEX, which doesn't oxidize, or we use copper for years and years. Actually, since World War II. Actually, before World War II, anybody know what they tended to use? They still use it in some parts of the Midwest. Galvanized steel. They do use copper pipe, but it's galvanized inside and outside. It depends on the water chemistry, okay? In the Midwest, they must have hard water out there, because I would think hard waters, the ones that have a lot of sulfates and stuff, would the zinc would hold up for 40 or 50 years. But the copper will hold up even longer, okay? Copper is found in its native state, and it's had, Michigan, it's had rain falling on it for millennia, right? And it's still there as copper. Won't be anymore because we have acid rain, but that's another story. So anyway, so we have black iron pipe, or as I say, if the fish can't breathe, you won't have corrosion, okay? You need free oxygen. And the O in H2O is not free oxygen, it's bound to the hydrogen. Unless you get very acidic or very caustic, and now actually very acidic, you can get some free oxygen, okay? And that's why acid waters tend to be a problem. I couldn't find a good piece of PEX in the lab. There was some a couple of weeks ago, but anyway. There are other well, there's another example I had. Before I get to that, let me show you an example. Like a few years ago now, it's 20, someone brought me a pipe, and they said it came from their fire protection system. It looked similar to this, except it was all rusty inside, okay? This actually has limestone scaling on the inside. This is a boiler system, and they didn't treat their water, or they over-treated their water, and they basically started precipitating out limestone on the inside of their pipes, and if you do it long enough, you can get hardening of the arteries, okay? It doesn't flow through well. Anyway, someone brought me from apparently a pretty good sized warehouse here in Boston, a pipe that looked just like that, except it was brown rust on the inside. And it was supposedly from their fire protection system, and they'd been having their annual inspection of their fire protection system, and they found the whole system, and this was like a half-acre factory. I mean, it was great big fire protection system, and they were all had clogged arteries. And they sent it to me, and they wanted me to do an analysis. And I looked at it, and rather than doing an analysis, I called them up and I said, "You guys have had a leak in your system, haven't you?" They said, "Yeah, how'd you know?" I said, "How long has it been there?" They said, "Oh, about 10 years. I said, "How big was it?" And they said, "Oh, it's a stream about a quarter inch going into a drain." And they figured, well, they just had makeup water filling up the rest of their system. Well, they no longer had a closed system. They had an open system. That quarter inch of water that they just figured will pay a bigger water bill was bringing fresh oxygen into their closed system on a moment-by-moment basis. And over the previous 10 or 20 years, they had clogged up all the arteries because it wasn't a closed system, it was an open system. And they wanted to know how I knew. Well, I knew because the principle is, okay, you can't get corrosion unless you got free oxygen, and it wasn't a closed system. So they had to be bringing in oxygen with something, and sure enough, they said, "Well, what do we do about it?" I said, "You buy yourself a new fire protection system because you can't afford to, you know, it's cheap. You can't flush it out." Okay, so far as that goes. Another example of how oxygen promotes corrosion. By the way, these two books they used to be like, I think I paid $40 for them. I used to recommend to the class till I learned that they give you like $100 budget for books or something. It's a joke, okay, whatever it is. But these two books are the Nalco Guide to Cooling Water System Failure Analysis, and the other one is the Nalco Guide to Boiling Water Cooler System. So if you work in a boiler room and you want to know all the different types of problems you can have, they're now about $150, but nonetheless, this is what's called splash line attack. This is a stainless steel beaker, and it was filled with some corrodant, you know, some water solution, probably had chlorides in it, so far as that goes, and they get pits right here. Why? Because the best thing to pit stainless steel is oxygenated chlorides. Okay? Chlorides will help break down the protective chromium oxide skin. Okay? If you have a practical nobility by a protective skin, if you break it down, well, in this case, you have chlorides present, and you can accelerate the corrosion by a factor of 10 to 100 times if you also add oxygen. Okay, this got to be sort of a problem for General Electric in the nuclear business, and some of you are nukes. Around the late 1970s, they had built all these 304 stainless steel commercial nuclear reactors, and the next thing they know is they're doing their inspections, the reactor safe end. What's the reactor safe end? Anybody know? Reactor safe end is this like 24 or 36 inch diameter pipe, like inch and a half stainless steel, and if you have to flood the reactor to shut it down with borated water, the safe end is the pipe through which you bring the flood of borated water to shut down the reactor in an emergency. Well, they had cracks in them. So who wants to flood your reactor with a pipe that's going to break and doesn't flood your reactor? Okay, so the Nuclear Regulatory Commission didn't like this either, these cracks, and they got in and they found that they were getting corrosion, stress corrosion cracking of stainless steels with, I think it was 1 part per million oxygen in the water and 1/10 of a part per million chlorine, okay? Or something like that. Well, nuclear reactor water is really pure because they want to keep the oxygen out, they want to keep the chlorides out. How do you measure really pure water? Anybody know? You haven't run a, none of you have been in it. You've been in an engine room. Megohms, right? You measure the conductivity of the water. And what's the best conductivity you can get? Or the lowest, the highest resistivity you can get? It's 18 megohms. If you were probably running at 14, right? Or something. I mean, it might be classified, but whatever it is, a commercial reactor would typically be running at about 14 megohms. 18 megohm water is absolutely, if you took absolutely pure hydrogen gas and absolutely pure oxygen gas and reacted them to get absolutely pure water with no impurities, it would measure 18 megohms. And typical in any commercial power plant, it doesn't have to be a nuclear plant, it can be a coal-fired plant, it can be a gas-fired plant, the water for the steam is going to be 10 to 14 megohms. Okay, and you probably had to do nowadays you probably have continuous monitors and plotting it out. Okay, yeah. The old ones they check about once a day and stuff, but they would check once a day, because if you start seeing 5 megohm water, whoa, okay, you may have just lost your reactor in terms of long-term corrosion performance. Okay, you wouldn't have lost it right away, but anyway, the resistivity measures all those salt. It's sort of an average of all the salt impurities and the oxygen. So what did General Electric do? They did a lot of things. It was about a $2 billion problem for them worldwide, and they studied stress corrosion cracking of 304 stainless steel in spades in terms of research. But one of the things they did is they started controlling the oxygen, because most of the damage was on shutdown. Okay, it wasn't when you're operating. Boiling water's got how much oxygen in it? Near zero, because all those little bubbles that come up are carrying any oxygen in equilibrium, and you got a nearly 100% steam bubble, and any oxygen comes out, and you can, by boiling water, you can sparge out all the oxygen that's in the water. And so one of the things they did is, before they would start up the reactor, they would have a pre-boiler that would boil the water, and they would circulate the water to get rid of all the oxygen in the water. And that's what they still do, because once you shut down, and when you come into port on a nuclear carrier or a nuclear sub, and you shut down the reactor, you basically have to do something to take care, and they put nitrogen blankets over it. The Navy actually uses something called, what's this, H2N2. Anybody know the name of that? Some of you must know the name of this. Hydrazine. So hydrazine is a great antioxidant. I guess if you're into health and all the antioxidant, drinking blueberry juice and stuff, this would be even worse, because this would kill you. But it's a great antioxidant. It would kill bacteria, big time. Okay, it's an antioxidant. Well, actually, I don't know if it would kill bacteria. You really need ozone to kill bacteria. Anyway, the Navy puts hydrazine above there, and any oxygen will react with the hydrazine. Commercial plants do it because hydrazine's too expensive. Okay, only the Navy can afford it. But commercially, they basically steam sparge, and they watch their oxygen very closely, because if there's no oxygen, you can't have corrosion, right? Let's see. Now, to prove also again that if you have no oxygen, you can't have corrosion. This is a plot that comes out of a book called Marine Corrosion, and it's actually not a bad book. I think it's out of print now, but this is the depth of the ocean in thousands of feet. So we're going down to 6,000 feet here, versus oxygen in milliliters per liter, which is in basically parts per million, if you will. Milliliters per liter is parts per million. So we're down here below 1 part per million oxygen. If you're down at a couple of thousand feet on the surface, you might have 6 or 7 parts per million oxygen. They also have the corrosion rate of steels. This is AISI 1010 and another steel, and pretty good correlation, right, between corrosion rate and oxygen concentration. Okay, so that's what causes. Now you can accelerate the rate of corrosion with other things like chlorides and stuff. I told you that stainless steel needs chlorides to help break down that passive layer. So my mother-in-law lived with us for 17 years, and it was kind of her job every night to clean the dishes. And one time she didn't have enough to fill up the dishwasher. She decided to take our stainless steel dinnerware and put it in some Clorox overnight to sterilize it. This is after, I mean, it used to bug me no end. She would turn on the hot water and just leave, after dinner she'd turn on the hot water and it would just run in the kitchen sink. She would never turn it off. It would just run for the next 2 hours. Okay, I just see the, but anyway. But anyway, this time she decided to put it in Clorox, and the next morning, of course, everything was pitted. Okay? So far as that goes. And I got to buy some brand new dinnerware. Another thing you can do to get rid of the oxygen is you can take it through a vacuum system. And so they basically, the commercial reactors, they actually will use steam to generate a vacuum through a venturi, and you spray the, either pump the bubbles out of oxygen, or you run the water through, and now you have more surface area and you get the oxygen out that way. We also store old aircraft. Where? Oh, actually, this is the next one. The next point. Pardon me? In Arizona, right? Did you say Arizona?
The desert.
The desert. Because the next point, which I've lost, where did I put my my little sheet? The point 4 is you need to get rid of moisture. There it is. Okay. Moisture provides the electrical pathway for chemical charge transfer. Corrosion is a chemical process, and moisture is a good way to transfer. You've got to have Kirchhoff's law, and you've got to have a circuit. Okay, and so if you're going to have cathodic protection of something, you've got to have a complete circuit, as far as that goes. And so we take old aircraft and we store them in the Arizona desert, because someday we may need those parts, right? And so that's where all the old B-52s were. You've seen the picture of when we had the SALT treaty or whatever, and they would take the wings off the B-52s, and so the Soviets could see by taking satellite pictures from space that we were destroying all our bombers that were in mothballs in Arizona. Okay, so that's why we store it there. And of course the Navy, being good corrosion engineers, they store everything they have right there in the water, right? In a chloride containing water. But anyway, it is nearly 70% or 72% of the Earth's surface, right? So moisture, it doesn't matter whether it's liquid or whether it's humidity, you're going to have a problem. Now the wet-dry conditions can accelerate the corrosion. I told you that typical corrosion rate of carbon steel is about 4 thousandths a year, and it could be 10 thousandths. This really depends on how many chlorides you also have around, and we can talk about that after the break. But let me first tell you the worst corrosion rate I ever saw of carbon steel was in Arizona. Okay, it was about a 1 or 2 acre warehouse, distributing warehouse. So it's right there on the interstate from California to, and so this was all the semis would come in here and they'd store things for a few days or a few weeks. They were building this warehouse, and in Arizona you don't usually worry about rain when you're doing construction, and so, but it does rain in Arizona every now and then, and when it rains it pours. Okay, so they were building this warehouse, and they had put a moisture barrier, because that's how you design roofs. They had put a moisture barrier in, and they hadn't put the top roof on yet, and they had some galvanized steel that was going through the moisture barrier, but it wasn't a perfect moisture barrier. In any case, the rains came while the roof wasn't complete, and these contractors, because in Arizona they don't usually worry about rain. Here in New England, if the rains came, well, first of all, they wouldn't have built it that way. They would have had some way to protect it from the rain, because we get rain every couple of days, and you don't want to get moisture trapped in your building. But basically they ended up in the ceiling of this warehouse with by the time they put the roof on 3 days after the rainstorm, and they had a vapor barrier down here, they had a little sauna in here. So it was nice and dry in the warehouse. It was nice and dry out here in the atmosphere, and here's your roof decking, and it was impervious to moisture, and then you had your vapor barrier down here, and then they had these galvanized hangers in here, and within a year they were seeing rust when they were doing some inspections up there. The galvanized steel had completely eaten up the zinc coating, and some of these hangers actually had corroded through. They were sheet metal, and some of them were corroding at 40 thousandths of an inch per year. I've never seen anything that rapid before. In fact, when they told me, before I went out there to see it, I said, no, you got to have something else going on, because the fastest you ever get is 10 or 20 thousandths. And what they were telling me and the samples they were sending me, I said, no, there had to be something else, because they were getting 40 thousandths or even 80 thousandths in some spots to destroy these hangars. Well, what had happened is they, night and day in Arizona, the sun goes, during the day, it gets hot in here, and all the moisture down here evaporates, and you get a very humid environment, and then the night comes, and that condenses, and the next morning, it's just it was a corrosion test facility, okay, that they had built in their roof, okay, and that's the fastest carbon steel corrosion rate I've ever seen. You could do sewage, you could do chlorides, you could do anything you want. This was the best. It was in Arizona. Okay, so why don't we take about a 6-minute break, 8:35.